A paper that was just accepted to Journal of Graph Theory. My co-authors on this work are Matija Bucic, Pat Devlin, Hendon, and Dru Horne. The theorem I want to talk about today, theorem 1, is suppose we have a graph, bipartite graph. So if G is bipartite, and M is a perfect matching, then M intersects at least half of the other perfect matchings in G. So we say two perfect matchings intersect if they share an edge. And for any bipartite graph and any perfect matching in that bipartite graph, it intersects at least half of the perfect matchings. Yeah, there has to be a perfect matching, otherwise the hypothesis is. I'm just going to write PM for perfect matching because I'll write it several times. PM's in G, and there's a unique case of equality, which is a cycle. Let's see, well, a union of cycles, you could have the different pairings between, if you have two different cycles, each one of them has two perfect matchings. And so there'll be, let's say there's two cycles, so there's four perfect matchings in total. And, well, yeah, maybe union is.
Yeah, you could do component wise.
Yeah, probably. Yeah, I don't.
Oh, I see.
Yeah.
Okay.
Right. Yeah. Yeah. You would intersect 3 out of the 4 in the case of 2 cycles. So this is right. Okay. And so this fails if the conclusion. So the hypothesis that it's bipartite is necessary. So for example, if we take K4, let me get one more color here. We have there's 3 matchings, and they're all disjoint. So any of them only intersects 1/3 of the matchings in the graph. And in fact, we can use kind of this. And in fact, there's a much more dramatic example that we get by sticking these guys together as follows. Here, I'll draw. So now we're going to have 4K vertices. And basically, we've taken one of these white edges and kind of opened it up. You'll see when I'm done drawing. So here we have 4K vertices. And once you choose one of these white edges in a perfect matching, the rests are forced. So this white perfect matching doesn't intersect any other perfect matching. And the number of perfect matchings is 1 plus 2 to the k. Because if you don't have any white edges, you can always choose either the yellow edges or the blue edges in each of these packages. So we have,
It's like it's a cycle of these things.
yeah, a cycle of where we've kind of stuck a K4 in this funny way on. Yeah. Yeah.
In this example, we have a lot of triangle.
Yes. Yeah. Yeah. It's right. If it's bipartite, then you always get at least every perfect matching intersects at least half the perfect matchings. If it's not bipartite, then it could be as small. It can be exponentially small proportion. Now, for non-bipartite, we also have a simple lower bound that's a corollary of Theorem 1. So here, let's say lower bound. So now we have any graph G and the perfect matching M. So here's our perfect matching in G, and there's some other edges as well. So there are, and let's say that, let me just say that the number of vertices is 2 times n. So we have V1 to Vn and U1 to Un. Now there are 2 to the n minus 1 bipartitions of the vertex set that respect this perfect matching. You don't care which one the first edge is in, but each of the other following edges, you can put one end in one side and the other end in the other side. So we have 2 to the n minus 1 And if you take any perfect matching in the graph, it's going to be respected by at least one of these bipartitions, because the union of 2 perfect matchings is a bipartite graph. So there has to be some partition where here you have a matching M. If you have any other matching M prime, there has to be some bipartition where both perfect matchings are going across the 2 sides. Now we know that, so for each partition, if there are k perfect matchings that intersects M, then we know that there have to be at least k, or there can be at most k perfect matchings that don't intersect M. So the total number of perfect matchings that don't so using Theorem 1, the total number of perfect matchings that don't, let me say that disjoint from M, is at most 2 to the n minus 1 times the number of perfect matchings that intersect them. Is that clear? This is just, we have 2 to the n minus 1 bipartitions, and we apply Theorem 1 in each of them. And so we get this inequality. Now there's a gap in the exponents here. This is like n here is half the number of vertices, and k is a quarter of the number of vertices. So it's, I think, an interesting and maybe not too hard problem. I don't know. It could be doable to close this gap for non-bipartite graphs. But this is what we've done on that. Now, I want to shift gears a little bit and talk about a different perspective on the same theorem. Yes?
It will be, if Z is not a cycle, but still a bipartite graph, can we get something strictly larger than half? Let's say 0.51.
Yes. So if it's not a cycle, it has to be larger than a half. And in fact, the values that you can take are dense in the interval 1/2 to 1. Yeah. And I'll say a little bit more about that in a minute and show how to get that, how to do that. Or just mention how to do it. Okay. So now I want to talk about derangements and permutations on graphs. So let's say that G is a directed, loopless, simple and finite graph. Say,
Thank you for saying finite.
Actually, the definition works for infinite graphs, but the problem that we investigate does not make sense. So let me just say finite. The bijection sigma on the vertices of G is a permutation on G. If for all vertices X, sigma X is in the closed neighborhood of X. And more strongly, it's a derangement if it's in the open neighborhood. So this is a permutation of the vertices or a derangement of the vertices that's further restricted by saying that if a vertex maps to some other vertex, if V maps to U, then the VU has to be an arc in our graph.
So if you write neighborhoods, is that
Ingoing and outgoing combined, or
This is out neighborhood. So
Out
maybe, yes, good question. But that's what I mean. It's just the out neighborhood.
that's close to neighborhood, right?
Yes, so for the permutation it includes X. For the derangement it does not include X. Now let me write P sub G for the number of permutations on the graph G. V sub G for the number of derangements. And the main quantity that we're interested in studying is the ratio between them. So D over P sub G is the ratio. Now, an equivalent formulation, we can get, let me write an equivalent formulation to theorem. I'll rewrite theorem 1, but have it about these objects instead of perfect matchings. So theorem 1 restated. This ratio D over P sub G is at most 1/2 with equality only if G is a directed cycle. So how does this work is we have some directed graph G like this. And we have on this graph we have some permutations. Here's one, which is a derangement. Here's another which is not the derangement. And here's a third, which is also not a derangement. Now we can map this graph into, let me write it underneath here. We can make this into a bipartite graph in an obvious way. We can make two copies of the vertex sets and have that. Now there's a direction left to right that we just copy from here. So if we have.
What do you mean by the graph is not a
This is a derangement. Like I'm just writing the cycles of the permutation. Yeah, so this one map.
That's the map you're drawing there.
That's the map that I'm drawing. This is the graph and this is the map. Yeah. This is these are the three permutations on this graph. This one is a derangement. This one is not. And that one is not. Right. So let me draw. On the left side of this line are graphs, on the right side are maps. Or I'll also have perfect matchings next to it. So A, B, C, A, B, C. So A has an out edge to B and an out edge to C. B has an out edge to C, and C has an out edge to B and A. And then you can also look at these horizontal edges. Now, if you have a permutation on the graph, it gives you a perfect matching on the, if you have a permutation on the directed graph, it gives you a perfect matching on the bipartite version. So here we have that one. Here, let's see, we have this one. And here we have this one. So the perfect matching corresponding to the permutation is avoids the horizontal edges if and only if the permutation it corresponds to is a derangement. Because the fixed points in the derangement correspond to, we're taking one of the edges of these perfect matchings. So it's easy to see these theorems are equivalent. So let me, but the perspective kind of leads to, I think, a different collection of problems that's maybe interesting. And this is also the setting that we were originally thinking about the problem in. So let me talk about some examples. Or really just one example, I guess, or one family of examples. This will be the blow up of a directed cycle. Well, I guess I could just mention really quickly that in this context, I'm sure everybody is familiar with the kind of classical application of inclusion-exclusion to show that the number of derangements unrestrained is something like 1 over E times, or asymptotic to 1 over E times the number of permutations. So this is some special case, and then what we can do is ask, well, can it be larger than 1 over E? The answer is yes, for example, for a directed cycle. But let me talk about the family of examples so we can see something a little more interesting. So there's a blow up of a directed cycle. I'll say D sub k comma L has k vertices per part. And L parts. So what we have are some parts with k vertices per each, and they're ordered 1, 2, 3, 4, just like a corresponding to the vertices of a directed cycle, and then it's complete from one part to the next. Like this. So the number of vertices is k times L. The number of edges so we have all possible edges between each consecutive pair. There are L consecutive pairs, so k squared times L. Now, how many derangements are there? So you map one vertex to one of its neighborhood, and then so there's k choices for the first one, k minus 1 for the second, etc. So it's k factorial times L. No, to the L. Yeah, that's important. K factorial to the L. How many permutations? So if you have, say, I fixed points in one of these sections, then you have to have I fixed points in all the sections. So what we can do is sum over the number of fixed points. I is equal to 0 to k, number of fixed points per part. And now we have to choose I vertices in each part. So that's k choose I to the L. And then the remaining k minus I vertices we have to map. So we get k minus I to the L. K minus I factorial. Yes, thank you. To the L. So we can simplify that. This is k factorial over I factorial to the L. So if we divide the number of derangements by the number of permutations, well, the k factorials cancel out, and what we get is 1 over sum from I equals 0 to k. What? Yeah, so when L is large, it's roughly half. Yeah, exactly. That's a very good point. That was going to be the next thing I say. Factorial to the L. So if L is large, any large, I mean, as you take L larger, you get something arbitrarily close to a half, because this is going to be 1 plus 1 plus 1 over 2 to the L plus 1 over 6 to the L. So you can get minus 1. So you can get arbitrarily close to 1/2 just by choosing L to be whatever suitable constant you want. And then take K to be your asymptotic parameter, and you can get something that's very close to L. On the other hand, there's a very interesting question, I think, for that doesn't really make sense, or it's not very obvious in the oh, actually, let me just mention that. So in our original, the paper that I'm talking about today, one of the things that we did is we showed that the ratios that or the numbers that you can achieve by looking at this ratio are dense between 1 and 1 over, or between 0 and 1 over e. And the way that that comes about is just by looking at uniformly random graphs with a fixed number of edges. And uniformly random graphs with a fixed number of edges. And this follows from some fairly standard probabilistic techniques. Now, there's a very recent paper on arXiv I just saw a few days ago. I need to look up the authors. This is the, yeah, here it is. And what they did is they look at they fix some blow up of a directed cycle, and then look at a random subset of this blow up of a directed cycle with a fixed number of edges. And in this way, they managed to show that you can achieve that the ratios that you can achieve here are dense between 0 and 1/2. So they extended our result was 0 to 1 over e, which you get by just taking a random subset of a complete graph. If you take a random subset of a blow up of a directed cycle, you can get any value between, or you can get arbitrarily close to any value between 0 and 1/2. So this is Alstoff, Bennett, and Christo. I'll just write it down. So there's, I guess, a more refined version of this result, or a question that's still open, I think, is it true that every rational number between 0 and 1/2 can be achieved as this ratio for some graph?
You mean 0 and
It's dense in 0 and 1/2, yes. I do mean that. Now, I'm also interested in the case where we fix G to be undirected graph. So here I'm thinking of an undirected graph as just being one where if you have a arc UV, then you must also have the arc VU, and then call this an undirected edge. And you can have the same definition works. And the conjecture is that the ratio should be extremal for the complete bipartite graph. So let me write the conjecture. G is an undirected graph on 2 n vertices. And with equality only. And so here this complete bipartite graph is actually a special case of this construction when you take L to be 2. And if you look at this expression, we have sum of I is equal to 1 to k of 1 over I factorial squared. Well, E is sum of 1 to infinity of 1 over I factorial. So this would, in fact, be a larger ratio than E. And you can check it also for small values. It's quite definitely the complete bipartite graph does give you a larger ratio than the complete graph. But we don't know if this is actually the extremal case for undirected graphs. And I think this is a question I thought about a fair amount and would be interested to see a solution. We do have some partial progress towards this. This is theorem 2. If G is undirected and bipartite, then the conclusion the conjecture holds. Okay. So, meaning that if you assume that G is bipartite, then in fact, and undirected, then in fact, the ratio for KNN is extremal. If there are any questions, I'll go ahead and show the proof, at least at theorem 1, and hope we'll see how the time works.
Maybe something. So what was the origin of this problem? Did you come up with this, or is it?
So Mo Hendon and Dru Horne were thinking about this, and Mo asked me. Dru Horne was an undergraduate at University of Georgia when I was there, and so Mo Hendon was working with him on this question, the conjecture, basically. And he said, well, here's a nice easy question, maybe you can solve it. And the answer was, no, I can't solve it, but we can do some other things instead. Yeah. Yeah. So I don't think anybody, I haven't talked to many people. I showed the result to Paul Seymour, and nobody has said, oh, this is a classic result, and you just look in your textbook. And so as far as I know, it's in fact new. And it just seems like some kind of natural thing. It's surprising that, yeah. No, they did know about us. This is actually based on our work. Based on our work in the sense that we analyzed random subsets of the complete graph, and they took the construction that we pointed out, that I explained, the blow-up of a directed cycle, and looked at random subsets of this directed cycle, and showed that, in fact, you could answer one of the questions that we put in our paper just by looking at doing this analysis. So theorem 1 is at most half of the permutations on G are a derangement. And also there's the case of equality, which I'll mention. So the basic idea is an obvious one. We'll construct an invertible map N invertible from derangements to non-derangements. Right, it's you want to show that there are more non-derangements than there are derangements. An obvious thing to do is to just construct a map from the derangements into the non-derangements. And so first, step 1 is choose V a vertex arbitrarily. Injective, yeah. That's what I mean. The injective map. And the way that we show it's injective is by showing that it's that given the output you can construct the input. Yep. Is it good?
Usually the invertible is injective and surjective, right?
No, only invertible. Not. It's not. I don't want the bijective map. I just want injective. Yeah.
Yeah. So that's just one.
Oh right. No. You're right. No. Okay. No, you're absolutely right. I was not thinking about it precisely enough. So injective. Yes. Okay. Good. No, you're right. I was being sloppy. All right, so choose a vertex arbitrarily, and the map that we construct will depend on this choice. Now let's look at some derangement. So here are you have some cycles. And one of these cycles includes V. So here's V. So what we're going to do is just map the cycles that don't contain V to themselves. And then we've got to do something different for the cycle that contains V, so we can only worry about, we only really have to worry about the case where we have some cycle that contains V. So the idea here is this goes to a permutation that looks like this, except we got to do something else here because we can't map this cycle to itself. Otherwise, we'll end up not with a. It'll be a derangement, not a non-derangement. And so now let's look at this cycle that contains V. Something like this. Now, in G, there's going to be other edges. So here, there might be an edge like that, or there might be an edge like this. So if you take an edge, say E, then this completes a cycle where all the other edges are, let me call this cycle C. So here's our cycle C is the outside part. Here's some edge that's not in the cycle E. And this edge E will give us some cycle. So here's the cycle it gives. I'll call this C sub E. And then it doesn't give a cycle on the other side. So it kind of chops off some vertices. And here is this, let me call this other one E prime. And this gives some other cycle. Here the cycle is on this side. And it chops off those vertices on that side. So what I'll say, since V is in C sub E, we call E a forward chord. Of C. And then E prime we don't care about. We're going to kind of ignore E prime for the most part. Because it's not a forward chord, because when you look at the cycle it completes, well, it chopped off V. And so one easy observation is if there are no forward chords, then C is the only cycle on this set of vertices. It doesn't have to. The only cycle on exactly this set of vertices. So there's other cycles on the set on subsets of the vertices. I mean, it's the only cycle that uses all the vertices. And yeah, maybe the just observation that every other cycle will avoid V is sufficient for that. But it's not the proof that I had in mind. But maybe that's good enough. Is that good enough? Because in particular, there will be no other cycle that contains the vertex V. So
I mean, that feels like it requires the same proof that you were going to.
Okay. So let's suppose that there's, well, yeah, let's suppose that there are two vertices, two cycles C. So here's C and C prime. So here's C, and then we have C prime. Well, C prime is going to at some point deviate from C, and then this is the first place at which it deviates is this forward curve.
What about, can't it be just going backwards in the cycle?
Then indeed the first edge would be so this here. Is a forward curve, yes, because it completes this here, completes this cycle that contains V. All right, so that's the proof of that. And so in this case, that if there are no forward chords, we just map the cycle to a set of isolated vertices. So now we can assume that there are forward chords.
I don't understand what you mean.
As you fix every vertex on the cycle.
We fix every vertex on the cycle. So here's our derangement. If this cycle has no forward chords, then this question mark is just going to be isolated vertices or fixed points. Yeah. Is that clear? Now, if there is a forward chord here, we'll do something different, because there could be multiple. There can be lots and lots of cycles that contain V on exactly this set of vertices, and in such a case, we need to be able to distinguish which one we're mapping from. But if there's only one, then we can just map it to a collection of fixed points, and we'll look and say, well, we know that this cycle is in, this cycle is in, and then you've got these other fixed points, and there's only one cycle on this set of vertices, and that had to be the one that we mapped. Yeah. So that's how we.
So hopefully we'll be able to determine that it should be just one cycle.
Yeah, it's because we mapped in all the other cases. We're going to map V. We're going to map this thing to a cycle that contains V and some other fixed point. So if V is not in a cycle in the image, then we know that it comes from one cycle. So it's important, but yeah, and it's not obvious from what I said so far. That in fact. So now we have forward chords, and I want to say that a forward chord is minimal. So here's put V at the top again. So here's some forward chords. And we'll say E is a minimal forward chord if, well, let me actually name the vertices. So let me put now, we'll call this V1, V0 is V, and then we have this fixed cycle C. As we go around, we'll say V1, V2, V3, V4. So this definition minimal will depend on the specific cycle that we're looking at. It's not an inherent feature of the set of vertices in this edge. So we say it's a minimum forward chord E, Vi, Vj, if for all E prime, Vi prime, Vj prime not equal to E. It's not, well, now if there is no, let me say that. If there is no E prime with I prime at least I and J prime at most J. So in this diagram, like V1, V3 is a minimal forward chord, V2, V4 is a minimal forward chord, but V1, V4 is not the minimal forward chord because there's chords that are living underneath it. Where underneath means these are the vertices that are getting chopped off by these forward chords. And this gives some partial order. So in particular, there's always going to be minimal forward chords. It's a partial order because we can look at the subset of the vertices that get chopped off. And being a minimal forward chord is, or if two chords are, if a chord A is less than a chord B, that means that the vertices that it chops off is a subset of the vertices chopped off by B. So we do in fact have minimal forward chords.
So you mean it's minimal with respect to the partial order you've written on the board?
Right, it's minimal with, there's a partial order, this defines some partial order.
Oh, okay.
So yes, it's not a, okay, I'm sorry, it's a little sloppy.
Do you require I prime less than J prime?
Yes, right, so this should be a forward chord.
One city just does it.
Yeah.
One
So forward chord, with its numbering, it's not exactly equivalent to I being less than J because you might have something like this. Like here's a forward chord. This could be a minimal forward chord. And indeed, I is not less than J.
Wait, I is
So yes, I is 0, and J is something. I is less than J. Maybe it is always
Yeah,
the
it
case.
should always be on the right.
So in a sense, it's a forward chord where the length of the other side not containing V is minimal.
Yeah, exactly. No, that's exactly what it is. Yeah. It's like every chord is chopping this cycle up into two pieces. There's the side that contains V, which is a cycle, and the stuff that's not contained V, which doesn't form a cycle with our new edge. And we're trying to find the minimal elements in terms of the number of vertices that are getting chopped off of the cycle. And so now the idea is we're going to look for the first minimal forward chord. So we have an ordering on the vertices. We've got V0 goes to V1, V2, V3, 4, something like this. And as we go around, there will be some forward chords. Maybe it's not minimal, but eventually we're going to come to let me draw it like this just so we have more room. After some time, we'll come to a minimal forward chord. And the first minimal forward chord is the first, we're ordering it by the first vertex that we see. And so we'll find the first minimal And what we're going to do is we're going to map our cycle to the union of the cycle that's completed by this first minimal forward chord together with fixed points for what we chopped off. So we're going to use only one edge that's not in the cycle that we're mapping from. So let me draw a little better diagram with some more vertices that are chopped off here.
Good question. So if we have a chord with which ends in V0, is that a forward chord?
Chord that ends in V0. Yes. Yeah. That is a forward chord because V0 is included in this cycle.
Okay, so the chords which contain V1 are all forward chords. Basically. V0.
The chords that
the chord contains V0 and it's a forward chord.
Same.
Then I guess then probably this definition is slightly wrong for minimal forward chord, right?
Yeah, maybe it is. Yeah.
I mean,
it's very likely, actually.
right. So it should be in the cyclic order ordering of these. We don't have we don't have smaller jumps.
Yeah, I think it's better just to order it as Sangel said. Look at the subset of vertices that is removed, and now this gives some way to compare two chords based on the subset relation.
So you want to minimize. You want to minimize J and then maximize I, but you change the numbering when you do the switch.
Right. Yeah, it's yes. It did take some. So here we've got. Let's suppose that this is our first minimal forward chord, and let me not make this V1, but I could say there's some path here, and then we get to minimal forward chord, and so we're chopping off these vertices, and we're keeping that. Now the claim is that we can reconstruct the original cycle from just this cycle together with these fixed points. Right? So first of all, the claim is there's no, so here's, let me call this fix, this set of vertices over here. There's no edge going from this interval into these fixed points. Because if we have such an edge, there must be some forward minimal chord that's underneath it, and this will be, either it's going to make this guy not be minimal, or it's going to be before VI. So what we do is we start at V. So let's suppose we're trying to reconstruct the cycle from our original cycle from this guy and a lot of fixed points. We know that we've got to stick these fixed points into the cycle that contains V. So what we do is start at V and we step until there's an edge that goes into the fixed points. There can't be two simultaneous edges for exactly the same reason. Now this one is smaller than that one. This is less under the partial order. So we can find VI plus 1. And similarly, you're never going to have a kind of, you're never going to leapfrog ahead underneath this edge, so you can, one at a time, construct the path inside the edge and then hop out. And then this is how we do it. Yeah? But, now we can say, so how do we know that the only case of equality is for the cycle? So first of all, if there are many cycles, if we ever have some derangement that isn't a complete cycle, that contains all the vertices, then we're never going to, in this map, we're never using the case where, well, let's keep these two cycles and map this one to fixed points, right? So here I've exhibited, what I'm going to try to do is exhibit some permutation that's not in the image of our map under the assumption that the underlying graph is not this directed cycle. So step one is suppose that there exists any any derangement that's not the complete, that's not Hamiltonian. Then you're going to have some derangement with multiple cycles, and you never use the permutation that keeps the cycle that contains V intact, but breaks one of the other cycles into fixed points, which is certainly a permutation. Because we can always take if we replace this guy, which doesn't contain V, with 4 fixed points, well, we definitely didn't use that because the only thing that we're doing is over here, the cycle that contains V. So at the very least, we can say immediately that there will always be some permutation that's not an image of the map if there's a derangement that's not Hamiltonian. So suppose that there's a derangement that has multiple cycles.
Okay. Yep.
Well, when we apply our map, we're only ever doing anything to this one. We never do anything to this one. So if we keep these 2 cycles and break this one into fixed points, that's an example of a permutation that's not in the image of our map.
But can't we? How do we know that we won't be able to invert like if you?
We know that we can invert the map. So that in particular, there have to be at least as many non-derangements as there are derangements.
Oh, but I don't see, like,
If you give me, so what's meant to be my certificate that this map is this permutation wasn't obtained from a derangement?
Ah, right.
Right. So you might have
So you may have this guy and this guy.
I mean, you're just giving,
Yeah,
you're
no,
just
no,
giving.
I agree. No, I agree. Yeah, that's a good point. Let me come back to that. Let me just treat the case that.
Sure.
Yeah, no, it's a very good point. So in the case that we have a forward chord, we're never mapping this cycle to all fixed points. Well, right, because of the observation that the only time that if there's no forward chord, if there's ever no forward chord, then we only have the one cycle that uses all those vertices. So in that case, we would map it to the fixed point. So if there's ever a forward chord for any cycle that uses the same vertices as C,
Right. So you could
then there's always a forward chord that uses, no matter what sex, even if you start with a different cycle on the same set of vertices, there'll still be a forward chord, because if there wasn't, well, there would only be the one cycle. Suppose there exists a forward chord for C. C is a fixed cycle that contains V. Then there's always a forward chord for any cycle C prime on the vertex set of C. Yeah. Hence, we will never map. We never see the permutation that maps exactly this cycle only to fixed points, because the only time we would ever do that is if we didn't see a forward chord.
Oh, so are you taking the identity permutation?
On that identity permutation on the set of vertices underlying that cycle. Yeah.
Which cycle?
C.
What's C? Sorry.
So this is C. This is C.
So you start with, are you starting with a vector? Or
You start with a graph.
a subgraph? Okay.
Right? And then we're looking at some derangement on the graph, and we're mapping it to something. The claim is when we look at this derangement,
We want to prove injectivity of the map even.
We want to prove strict injectivity.
we want to prove surjectivity, or that it's not surjective unless it's a directed cycle.
So I guess the thing that I'm slightly struggling with is if you start with the arrangement and map to somewhere.
So if we're looking at the image, if we look at something in the image of this map, and V is a fixed point,
Okay.
then the only time that happens is if there's a unique cycle that contains the set of fixed points.
Yes.
Right? Hence, if there's not a unique cycle that contains exactly that set of fixed points, we never see that exact permutation where this collection of vertices is mapped to fixed points.
So you need to find.
So if we ever see V as a fixed point like this, we ever see this, then we know that this cycle is in fact the only cycle on this. So if there's ever a forward chord here, we know that there's more than one cycle, or we don't know that there's more than one cycle. If there's a forward chord, we know that there's not more than a forward chord. There's only the one cycle. So, but this tells us that there's only one cycle up there. So if there's more than one cycle on this set of vertices, we never see this in the image.
So if there's more than one cycle containing V, then you can find then your map is not surjective. I agree with that. But anyway.
So and that happens whenever there's a forward chord on the set of vertices underlying some cycle in the middle.
No, wait. You need.
Or you can say that if there are two directed cycles,
This is I'm not done yet, but do you agree that if V is a fixed point, that means that based on the map that we've defined,
then the set of fixed points should have a unique cycle.
Should have a unique cycle on it. So in particular, if you ever have a set of vertices that has more than one cycle containing V,
yes,
then it can't possibly
then
give this permutation. And in this case, we've identified some permutation that's not in the image of the map.
I agree with that.
Okay. The other case is, well, maybe it's not the direct, maybe if we look at the set of vertices underlying our cycle that contains V, it's not the directed cycle, but there's still a unique directed cycle. So this could happen if, for example, I'm just going to draw it over here. This could happen if there's some edges that are not forward chords. Something, well, now we need a chord that's not a forward chord, so let me say like this. So in this case, this is not a directed cycle, but we do map it to, we would map it, in fact, to a collection of fixed points. Right? Like if this is exactly the graph on the vertex set induced by the vertex set underlying our cycle C.
Oh, so if that's what the graph looks like, if you've got a derangement, and that's what the graph looks like if you were based on the cycle containing V.
Right. So now there's no forward chord, but it's not a directed cycle.
Yes.
Yep. Then, in fact, the permutation that looks identical to this derangement except on the set of vertices and is a fixed point on the set of vertices does appear in the map, in the image of the map.
Yep.
But now we have another one that doesn't, which is this cycle together with these fixed points out here. Right.
I see.
Yeah. So in fact, right. Anyway,
if you find any, yeah.
I'm already 5 minutes over time. But this
All
is.
right, thank you very much.
For given perfect match M and it intersects how many other perfect matchings?
For triangle free, but not necessarily bipartite. No, I don't know anything about that. So maybe that's, yeah, the only counterexample we have has lots of triangles. Yeah. So I don't know anything about that. Yeah.
Is there any conjecture for a hypergraph version of this?
I haven't thought about it. I'm not even sure how to define it for hypergraphs. Oh, and the perfect matching setting. Yeah, that would make sense. I don't know anything about that. It might be worth thinking about and coming up with. I haven't thought about it seriously. Yeah.
I'm wondering about some polytope version where, like, if you have a bipartite graphs and perfect matching, you can make a perfect matching polytope inside some space, and then this gives you the property that when you pick any extreme points on this polytope, then you have at least half of the other extreme points in some union of hyperplanes. Right. And like, this is strange property, and maybe some other polytopes might have the same feature.
Yeah, that's interesting. Yeah.
Have you thought at all about the proportion that, so if you wanted to have at most one fixed point, say, or like you sum down on the number of fixed points?
No. So I think that any question that you could ask about permutation statistics, you could make into an extreme order question on graphs, and yeah. And maybe some of them are not interesting, but maybe some are. For example, the lower bound on this quantity that lives between 0 and 1/2, it's not interesting because it's easy to come up with a graph that has lots of permutations and non-derangements. But on the other hand, the upper bound is more interesting. Right. So I'm sorry I didn't get to show the proof of theorem 2. It's completely different. It uses some, it's a lot more simple in some respect. It's just Cauchy-Schwarz applied to the right set of calculations on the permanent. So, very much more, like this I think of as being kind of a graph theory proof, my first graph theory proof. But the other one is more like a typical extremal combinatorics thing. Theorem 2.
Any other questions? Is that a single speaker there?